Hey guys, today we're looking at 8.5, which is our last new topic. So what we are doing is volume again, but this time it's cross sections method. So basically what we are looking at, and I've got some YouTube videos here that we can look at, we're going to take a specific shape and that's going to determine what our volume is going to look like. So let's start with a rectangle. And the first thing I want to do is draw a picture of a rectangle, just so we remember what it looks like. In a rectangle, you've got your base and your height. So the area for a rectangle is just area is equal to base times height. So basically what we're doing is this. So whatever our graph is going to be considered the base of our shape, our 3D shape. And so what we're doing with our rectangles is we're going to construct a bunch of rectangles next to each other that are going to be the 3D part, and they're going to help us determine the shape of this figure. And so that's kind of how we get our 3D shape, our volume this time. So just like we did in our last one, we're going to take that area formula and we're going to adjust it with our integrals. So if I'm talking about the area being the base times the height, well, the base is our curve. So my volume here is going to be from A to B of the top minus the bottom for my base, and then times a height with a dx. And when you're dealing with rectangles, it'll always tell you a rectangle of height something. And so that's what's going to go right there. Alternatively, you also can pull it out and put it in front of your integral if you wanted to. So next, let's look at squares, which is going to be pretty similar. If we have a square and it says side S, so all the sides are S, well, the area is just the side squared, right? Side times side, so side squared. And we're looking at that same kind of visual, so we're going to adjust our area formula to create a volume formula using our integral. So our volume is going to equal the integral from A to B of our top minus bottom. That's our S from the square. And it's going to be squared because we have S squared. And then put a dx on the end of it. All right, the next shape we're going to look at is a semicircle. So a semicircle looks something like this, and it's going to have a radius r. So the area of a circle is pi r squared, so the area for a semicircle is 1/2 pi r squared. And that r is going to be our base. So we had the base with the rectangle, the s, for the squares, and that R is going to be our curve. So let's look at what this one looks like with our YouTube visual. Pretty similar. So remember, whatever curves we're looking at, that forms the base of this kind of like 3D figure. And so now we're taking a bunch of semicircles. So it makes this 3D shape right there. Okay, so adjusting our formula, and I'm actually going to come up here and do some side work before I give you the final formula. So it's going to be 1/2 pi r squared. So if I'm looking at the volume, oh, let's get the pen back. We'll move that, there we go. So the volume is going to equal our 1/2, so we're going to go from A to B of that 1/2 pi, and then our r is the top minus bottom in that whole thing. Oops, sorry. Let's come back. Let's talk about this again. Okay, so what we are doing here, volume is equal to, we still have our 1/2 pi, integral from A to B, and then our r. That's what's going to be a little bit different here. So our r is half of the base. So if my whole figure is the top minus the bottom, my r is actually going to be 1/2 of the top minus the bottom, and then square it. And then put a dx. And I want to clean this up a little bit, so I'm going to go ahead and move that 1/2 pi out. So I'm going to have v is equal to 1/2 pi integral from a to b of a, and then I can distribute the square to the 1/2 and the top minus bottom. So 1/4 and then top minus bottom squared dx. And that 1/4 can come out as well, which gives us our volume is equal to 1/8 pi integral from a to b of the top minus the bottom squared dx. So we had to do a little bit of extra to get down to our formula. If that confused you, you don't always have to know why the formula works. This is the formula that we're looking at though, and this is the explanation for why that's the formula. Okay, let's look at some triangles. Let's get a purple in here for Richardson. Okay, so if I have an isosceles right triangle, so that's a right triangle, and isosceles means that the two sides that are not our diagonal are equal, and we're going to say that they're s. So to find the area of a triangle, we have 1/2 base times height, but the base and the height are the same this time, so it's just going to be a 1/2 s squared. So that s is going to be our base. So let's go ahead and look at the YouTube visual for this one. So same shape as all the other visuals. And now we're making some triangles. So these are not right triangles. This one is actually the next one we're going to look at, the equilateral triangle, but it works the same way. And now we're making a bunch of triangles. And that's how we're going to get our 3D shape. Okay, so if I have 1/2 s squared, I would have the volume is equal to, and I'm going to put that 1/2 on the outside, the integral from a to b, and the s is the top minus bottom squared dx. All right, and our last formula here is equilateral triangle. So that's a triangle where all of the sides are the same. And you may not remember this formula, but the area for an equilateral triangle is the square root of 3 over 4s squared. So my volume, I'm going to have that square root of 3 over 4 on the outside, the integral from a to b, and that s squared is what's going to be my top minus bottom squared dx. So those are all of my formulas. So you'll notice that a lot of them have pretty much the same base. It's got the integral top minus bottom squared for all 4 of these. They're just adding some extra things in front. The only one that's a little bit different is our rectangle, because you're not squaring the top minus bottom. So that one would be a little bit different. But you can use that to your advantage. Work smarter, not harder. And if you ask you to find any of the green ones, you really only have to find the integral once, and then just multiply it by the different things that are out in front here. So when you think about it, yes, it's a lot of formulas, but they're all very, very similar. Okay, so example 1, we're going to do a bunch of practice with these. And to make this video go a little bit quicker, I've already drawn our graphs over here. So we're setting up the integral to find the volume of the solid whose base is bounded by the equations y equals negative x squared plus 4, which is my blue parabola, and y is equal to negative x minus 2, which is the red line. And we've got our specific cross sections. It says that they're perpendicular to the x-axis. So that means that we're going up and down here in our little area. So if we're going up and down like that, it does mean it's going to be a top minus bottom. If it says they're perpendicular to the y-axis, that's going to be our right minus left. So we're looking at the top minus bottom, so I'm going to go ahead and figure out what the top is, and that's my negative x squared plus 4. My bottom is my negative x minus 2. So if I do the top minus bottom, it's a negative x squared plus 4 minus, oops, put the parentheses too early, minus a negative x minus 2. So a negative x squared plus 4 plus x plus 2, which is going to give me a negative x squared plus x plus 6. So we've already simplified that part, so that's going to be easier to plug into all of these because that top minus bottom is going to be the same for all of these parts. The only other thing that we really need to know is our a and our b. So how far from the left and how far to the right. So it looks like we're going from -2 to 3. Okay, so squares is my red formula up here. So if I'm finding the volume for squares, it's the integral from a to b of top minus bottom squared dx. And so let's just plug in our top minus bottom and our a and b. So the volume is equal to the integral from -2 to 3 of my negative x squared plus x plus 6 squared dx. And that would be the integral using square cross sections. All right, equilateral triangles is the same thing. It just has a square root of 3 over 4 in front of it. So my volume here is going to be the square root of 3 over 4 integral from a to b of top minus bottom squared dx. So we're looking at the square root of 3 over 4 integral from -2 to 3 of a negative x squared plus x plus 6 squared dx. And there is my volume. Rectangles of height 1. So that's what I was talking about. It's always going to give you the height right there. So I'm going to have the volume is equal to the integral from a to b of top minus bottom times the height dx. So my volume is equal to the integral from -2 to 3. My top minus bottom is that negative x squared plus x plus 6. My height is 1 in dx. Technically for this one, you don't have to write that one. Your height's not always going to be 1 though, so I would just get in the habit of always writing that height so that when it changes, you don't forget it. Isosceles right triangles with one leg in the base. So our isosceles right triangle is that 1/2 in front. So it's the volume is equal to 1/2 the integral from a to b of top minus bottom squared dx. So our volume is going to equal 1/2 the integral from -2 to 3 of our negative x squared plus x plus 6 squared dx. There is my volume with the isosceles right triangles. And the last one for this one is semicircles. And so semicircles is that one that's got the 1/8 pi. So if you're thinking circles, think pi. So volume is equal to 1/8 pi, the integral from a to b of the top minus bottom squared dx. So 1/8 pi, the integral from -2 to 3 of a negative x squared plus x plus 6 squared dx. And so once again, these notes, we're going to practice setting up these integrals because I know you already know how to do the integral. What we need to practice is setting up these area and volume integrals that are a little bit different and have the different formulas than what we're used to. All right, let's look at example 2. Set up an integral to find the volume of the solid whose base is bounded by these equations and whose cross sections are perpendicular to the y-axis. So that means that we're going this way, and that means it's going to be a right minus left. So if it's a right minus left, that means that I need to figure out what my right side is and figure out what my left side is. So let's start by taking that y is equal to negative x squared plus 3 and solving it for x. So I'm going to subtract 3. So y minus 3 is equal to a negative x squared. Then I'm going to divide by that negative. So now I'm looking at 3 minus y is equal to x squared, and I'm going to take the square root of both sides. So x is equal to plus or minus the square root of 3 minus y. And what's going to end up happening is our right is going to be that positive square root of 3 minus y, and the left is that negative square root of 3 minus y. So that's how I'm getting my right and my left. So if I subtract them, I've got the square root of 3 minus y minus a negative square root of 3 minus y changes to plus. So my right line minus left is 2 square root of 3 minus y. That's what we're going to look at. And then I need to figure out how far down and how far up I'm going. So the c and d, the bounds that I have. So I'm going down to negative 1, and I'm going up here to 3. So we've got all the parts that we're going to plug in. Now let's start plugging them in. So if I got squares, that volume is the integral from c to d of the right minus the left squared dy. So I'm taking the same formulas that we had up here. I'm just replacing the c, a and b with c and d, and top and bottom with right and left. So it's the same formulas. So my volume is going to equal the integral from negative 1 to 3 of my right minus left, which is that 2 square root of 3 minus y squared dy. All right, equilateral triangles. Equilateral triangles is the one with the square root of 3 over 4 in front of it. So my equilateral triangles is going to be the square root of 3 over 4 integral from negative 1 to 3 of the 2 square root of 3 minus y squared dy. Rectangles with a height of 2. So that one, I'm just going to go ahead and plug it in instead of writing the formula. It's just going to be the integral from negative 1 to 3 of that right minus left. So that 2 square root of 3 minus y times my height, which is 2, and then a dy. So that's where I was talking about. You still have to have that height there. Isosceles right triangles. That's the one that just has the 1/2 in front of it. So negative 1 to 3 of that 2 square root of 3 minus y squared dy. And semicircles has the 1 over 8 pi integral from negative, or not negative 3, negative 1 to a positive 3, 2 square root of 3 minus y squared dy. So there are all of my integrals for that example. We got 2 more that we're going to look at, get some more practice with getting all of these integrals set up. So we are looking at perpendicular to the x-axis. So that means perpendicular looks like this, and it's going to be a top minus bottom. So my top is that x plus 1. My bottom is the x squared minus 1. So I've got x plus 1 minus x squared plus 1. So I'm looking at a negative x squared plus x plus 2 for my top minus bottom. And it's going from a negative 1 to a 2. So it's going from this point over to this point. So I've got all the parts. Let's plug them in. So squares, I'm going to have the volume is equal to the integral from, oops, that should be a negative 1. To 2. So negative 1 to 2 of my top minus bottom. So the negative x squared plus x plus 2 squared dx. Rectangles with a height of 3. I'm going to go from negative 1 to 2 of that same negative x squared plus x plus 2. Not squaring it this time, but multiplying it by the height of 3. Semicircles is that 1/8 pi integral from negative 1 to 2 of the negative x squared plus x plus 2 squared dx. And equilateral triangles is that square root of 3 over 4 integral from negative 1 to 2 of a negative x squared plus x plus 2 squared dx. And last one, this time we are perpendicular to the y-axis again. So that means that we're looking at it going this way, so it's going to be a right minus left. So the right is the x equals 1 minus the left, we need to change the equation. So if I have y is equal to x cubed, that means x is equal to the cubed root of y. So 1 minus the cubed root of y is what we're looking at for our right minus left. And then our c and d, how far down does it go and how far up does it go? So it's going from 0 to 1. So I've got all the parts. Let's write some integrals. So squares, my volume is going to equal the integral from 0 to 1 of my right minus left. So 1 minus the cubed root of y squared dy. Rectangles with height 1, I'm going to have the volume is equal to the integral from 0 to 1 of my base, which is the 1 minus cubed root of y, times the height, which is 1 dy. Semicircles has got that 1/8 pi integral from 0 to 1 of 1 minus the cubed root of y. We are squaring it again. And equilateral triangles, that's got that square root in it. So we're going to have the volume is equal to the square root of 3 over 4, integral from 0 to 1 of 1 minus cubed root of y squared dy. So you've got all of your formulas up here, all of the formulas walking through the differences. Remember that the rectangle is the only one that it's not squared. And then the semicircles, isosceles, and equilateral triangles all have those different things in front of the same integral. That's the top minus bottom squared or the right minus left squared. All right, so that is volume with cross sections method. You do have a Go formative that goes with this for homework, so make sure you get started on that. If you remember, if you have any questions, you can ask me in class, send me an email, or come to tutoring. So you guys get started on the Go formative and have a good day.